Okay, welcome to lecture 6 of Unit 3, Topic 2, Power Dissipation. This video will be covering the main ideas of Chapter 9.3 of Book 1. You should complete this reading before class. Here are your learning intentions and success criteria for this chapter. Please pause the video and attempt to complete the knowledge and skills table. All right, so hopefully we've done that. So seeing here, we want to be able to explain how the use of electrical energy is known as power dissipation, and then calculate that power that is being used. So we need to be able to define the idea of power dissipation, and we need to be able to calculate the power consumption for both series and parallel circuits. 2 bits of knowledge. Well, firstly, what is power dissipation? If we don't know, it's pretty hard to define it. The second, how do I calculate power dissipation? So we need to know some formulas. So what is power dissipation? Um, when electrical energy is present in a circuit, it's not doing anything. Okay, that electrical energy needs to be converted into other forms, kinetic energy, light energy, heat energy, for example. And you probably have some of those devices around your room right now that are doing those exact things. This conversion of electrical energy is called power dissipation. Now, when this conversion occurs, charge is being moved across a potential difference. Remember, that's our voltage. And that was the definition for electrical work, moving a charge across a potential difference. Okay? Now, if we connect that to our definition of power, which is the rate of work, we can then examine the rate of electrical work. So here are our 2 formulas. We can see that one's P equals W over T, power equals work over time. Our other is work equals voltage times charge, moving a charge across a difference gives us energy. And so we've replaced this, we get that power must therefore equal the voltage times the charge that we're moving divided by the time. And the ratio of charge and time is our definition for current. So therefore, power equals voltage times current. Now, there's a couple of formulas that we can use for this. Our first is this one we may have seen earlier before. There are 2 formulas from the formula booklet, and we can derive a third. Now, this one, power equals voltage times current. Nice and easy. If we have those 2 bits of information, such as from a voltmeter and ammeter, we can then use it to calculate. Remember, power is in watts, joules per second. Voltage is in volts, and current must be in amps. There is a second in the formula booklet, and we can see here it's current squared multiplied by the resistance of the element. So if we know the current, we know the resistance, we don't necessarily need to know the voltage. This comes about by using Ohm's law, the V equals IR formula, to then substitute into the first to derive the second. So these 2 are given to you. There is a third, though, where we can substitute I equals V over R. And now we've got 2 interesting formulas because it's a bit of a contradiction. One is saying that as resistance increases, power usage increases. But the second formula, or the third formula here with the second one with resistance, the third formula here says that as resistance increases, power must decrease. Now, this is a challenge question in your textbook, chapter 9.3. I would really encourage you to try this question and understand it, because this would be a good example of a question on the end of your exam that could potentially ask you to explain power dissipation. Let's have a look at some simple examples. So, making sure my pen works. Yep. Calculate the power dissipated by an electric drill operating from the normal 240 volt AC supply and drawing an operating current of 1.60 amps. So, nice easy one. We have here a voltage of 240. The fact that it's AC does not change what we're going to be doing. And we have our current here of 1.60 amps. Now, if we take the 2 together, P equals IV equals 1.60 times 240. Everything was in SI units, and we can work that out. I should have probably had a calculator up and ready. 1.6 times 240, and we get that this is equal to 384 watts. Now, This has 3 sig figs. It has been given to us that 0 is a defined 0. This has 3 sig figs, 1.60. So therefore our answer can have 3 significant figures, so that's okay. Let's have a look at B. Calculate the monthly energy used by a television for a power rating of 110 watts that is operating for 6.5 hours. So we have here a power rating of 110. We want to know energy, and we have a time of 6.5 hours. Now, time here is not given in our SI unit, while power, remember, is equal to energy divided by time. So since we need energy, by the way, the formula that gives you in the textbook, I believe, is work divided by time. But remember, work is just energy used. And here we're saying, hey, it's energy used. Well, so therefore, it's the same thing. So remember, work is always energy. So we're going to have to convert this to seconds, and then we can figure out how much energy is used in a day, and then work out how much is used in a month. So let's figure out how much seconds is in a month according to this. So to convert seconds into minutes, we multiply by 60. To turn minutes into hours, multiply by 60. Now, normally we do times 24 because there's 24 hours in a day, but here our question says we've only got 6.5 hours of usage in a day. So times 6.5, and then we can multiply it by the number of days in a month. Now, some of them have 30, some have 31, one has 28 except for a leap year. The average is about 30. The most common one anyway, the mode is 30. And if you add them all up and divide by 12, you get a value that rounds off to 30. So let's just use 30. So that'll be our time. So now if we rearrange this, we get that energy equals power times time. Power was 110 times 60 times 60 times 6.5 times 30 equals, let's go back to my calculator, 110, 60. How many zeros is that? 1, 2, 3, 4, 5, 6, 7. Rounded off, we get 7.7 times 10 to the 7. Yes, 7 joules of energy. We could write this as 77 megajoules. That would be acceptable as well. Note our time has 2 sig figs. While this has 3, we always go to the smallest number of significant figures. Now, in terms of working out the power dissipation for circuit analysis, any circuit analysis question that you have where you have both the voltage and the current, you therefore can use this formula to work out how much power that element is using. If you have an equivalent resistance and you know the current running into it, or you know the voltage that is used up by the element, you can again use the voltage and the resistance, or the current and the resistance, to work out the power used by that equivalent circuit element, and that would still be the same if you've simplified it down for saying, hey, this section of, say, objects in parallel, objects in series, and how much is being used. All right. So to finish off, what we've looked at today, we've looked at what electrical power dissipation is, and we've looked at how to calculate the power drawn by an electrical current. For your entrance slip to class, please complete questions 1 to 6 in chapter 9.3, check your learning, and copy your answers to the 3.2.6 space on eLearn. Thanks very much. Have a great night.